We have the following recursive algorithm, and here we're assuming that needle 1 contains n disks where n is greater than 1. So the first step is that we would move the top n minus 1 disks from needle 1 to needle 2. And we're going to have to use needle 3 as the intermediate needle. Once we moved all those disks, then we can move disk number n from needle 1 to needle 3. And then finally, we would move the top n minus 1 disks from needle 2 to needle 3, where we would use needle 1 as the intermediate needle. That's it. It's a 3-step algorithm, but since it is a recursive algorithm, we're going to see that there is a bit more involved in order to move those top n minus 1 disks, because if we want to move the n minus 1 disk, we have to deal with the top n minus 2 disks and so forth. So we also have to change which needle is the intermediate needle depending on where our source needle is, our destination needle is. So the needle that's left over would be the intermediate needle. Here's our Java code for handling this problem. And we see it's just a couple lines of code. It's pretty straightforward, actually. I want you to take note of the parameters. So the first parameter is the number of disks that we need to move. The second parameter is the starting needle. So in our original method, we're starting at needle 1. The third parameter is the ending needle. So that's needle 3 in this case. And then our fourth parameter is the intermediate needle. So that's needle 2. So we're essentially saying that the first needle is the source needle, the second needle is the destination needle, and the third needle here is our intermediate needle. So let's look at the algorithm, or look at the code. Here we're saying checking if n is greater than 0. So as long as there is a disk that we still need to move, we first call move disks for the n minus 1 disks. We're going to move from needle 1 to needle 2, where needle 3 is going to be the intermediate needle. We're then going to print a statement that says to move disk n from needle 1 to needle 3, so that's the second line of code is doing. And then the last line is saying that we're going to move the top n minus 1 disks again, but we're going to move it from needle 2 to needle 3, and needle 1 is going to be our intermediate needle. Now for this algorithm, we're not going to worry about the running time of it, but what we do want to take a look at and what we're curious with is how long would it actually take to move all 64 disks from needle 1 to needle 3? If the universe is supposed to come to an end when this is done, it'd be nice to know when that's supposed to happen. Well, let's start with a simpler case, and then we'll move back to the 64 disk problem. Let's say we go back to the case where needle 1 has 3 disks. What we found is the number of moves needed to move everything from needle 1 to needle 3 was actually 7. And the way we got that was it ended up being 2 power 3 minus 1. So 2 power 3 is 8. 8 minus 1 is 7. Now, if we go back to our 64 disk case, so if needle 1 had that, we would find that the number of moves needed is 2 power 64 minus 1. So how many moves is that? Well, we're going to do a little estimation. So we know that 2 power 10 is 1024, and we're going to say that's pretty close to 1000, which is 10 power 3. So if we use this approximation, what we would have is that 2 power 64 is, well, that's 2 power 4 times 2 power 60, and 2 power 60 is going to be 10 to the 18th power. How do we get that? Well, 2 power 60 means that we're going to have 10 power 3 6 times based on our approximation. So 10 power 3 6 times is 10 power 18. So 2 power 4 times 10 power 18 turns out to be 1.6 times 10 to the 19th power. Now, we got the number of moves, but we want to know how much time this is actually going to take. So the number of seconds in a year is about 3.2 times 10 to the 7th. So keep that number in mind. And let's suppose that the priests are able to move one disc every second without any rest. These are super buff priests. They're very strong. They can move a disc every single second. So what does that give us? Well, what this means is we have 1.6 times 10 to the 19 moves. So we're assuming one move per second. So that also means we have 1.6 times 10 to the 19 seconds. But what does that come out to be? Well, we can break this up a little bit. This gives us 5 times 3.2 times 10 to the 18. And then we'll factor out the 10. So this actually turns out to be 5 times 3.2 times 10 to the 7 times 10 to the 11th. Then we'll move the 5 over. So we get 3.2 times 10 to the 7 times the quantity of 5 times 10 to the 11th. So what that means is the time to move all 64 disks is about 5 times 10 to the 11th power years. Okay? That's a long time. How long is that really? Well, let's put things into perspective. So it's estimated that our universe is about 15 billion years old. So that's 1.5 times 10 to the 10th power. Okay? So what does that mean? Well, we said that it would take 5 times 10 to the 11th power years. But if we did some math, we'd find that's 50 times 10 to the 10th power, which is approximately 33 times 1.5 times 10 to the 10th power. And what this means is our universe would last about 33 times as long as it already has. We've already gone through 15 billion years, and we got about another 33 times that amount. So I would say those priests are moving those disks for a very, very, very long time. Okay, so we know the universe is not going to be coming to an end anytime soon. That's great to hear. So here's another question to ask. How long would it take for a computer to generate all the moves to move the 64 disks? You might think, well, it shouldn't take too long, right? Well, let's just make a couple assumptions here. Let's assume that a computer can generate 1 billion moves every second. So that's 10 power 9 moves every single second. So how many moves can the computer generate in a year? Well, we've already mentioned that there are 3.2 times 10 to the 7th power seconds per year, right? And we already mentioned that we can do 10.9, or not 10.9, 10 power 9 moves per second. So we could generate that many. So we just multiply those together and we get 3.2 times 10 to the 16th power. So that's how many moves we can generate in a single year, 3.2 times 10 to the 16th power. Okay, well, we have 2 to the 64th power moves, right? Okay, so we have 2 to the 64th power moves, and we've already said before that's approximately 1.6 times 10 to the 19th power. So if we factor that out a little bit, we would get 1.6 times 10 to the 16th times 10 to the 3rd. And that means that would give us 3.2 times 10 to the 16th times 500. What that means is it would take 500 years for a computer to generate 2 to the 64th power moves if we are dishing out 1 billion moves every second. So I don't recommend running this program to generate all 64 disks. Try to generate all the moves to move 64 disks. You will not last long enough to see the end of that. So that also should give you an idea of how long this algorithm is. Although we don't have an asymptotic running time in O notation, we can tell that this is going to take a very, very, very long time.